The two new topics and ideas that we're going to learn in this chapter are these. So write down here at the top that our main new idea is to understand standard deviation of slope. Okay, so that's a big thing. We have taught standard deviation. What is the idea of just standard deviation in general? Standard deviation in general represents a what? Good, good. Standard deviation represents this average distance from the mean. Okay, so that's what standard deviation is doing in general. So what happens is when we have standard deviation of the slope, that ends up being a type of deviation from the predicted slope. Okay, so that's where we're heading for that one. And let's actually talk about that here in terms of this printout. So this is a computer printout of analysis of trees. And what is this data comparing? And you see on this picture what this data is referencing. Good, 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 good. It is volume, referencing volume versus height. Which of those do you think is the explanatory variable? Height, very good. Height would be your explanatory variable, and then of course your response variable then is the volume. Okay, good. They have then used this coefficient to create this equation right here, okay, to create this regression equation. And so what we've got is the predicted volume is negative 87.1 plus 154 times the height. So the slope is 1.54, the y-intercept is, okay, so let's talk about that in context. That is saying that, what is the slope telling you in context? And this is height in feet, and we'll just say cubic, I don't know, so whatever units, let's just say units in general. So, tell me this height in words, your context. Good, good. For every 1 unit increase in height, the volume unit increases 1.54. So the volume is increasing 1.54 units as the tree increases 1 unit in height. And I don't know if we understand what the units are here. Okay, very good. And here's what I'm wondering. If the y-intercept occurs when height is 0, y-intercept occurs when x value is 0. So that means this is gone. Tell me your real-life interpretation, a sentence to interpret the y-intercept. What is that saying? Yes. So let's talk about the realistic or the plausibility of that. It is saying that when the tree is 0 units tall, that the volume of the tree is negative 87.1 units. Okay, is that plausible? Why not? You cannot have a negative volume. So again, we see an instance where the y-intercept is not realistic, and the reason that the y-intercept is not realistic is because our data was probably gathered in this location, and this is far away from where our data was collected. What is it called when you make an inference far away from where the data was collected? Yay, good. Extrapolation. Okay, so that is why the y-intercept rarely is plausible. Okay, so let's look down here at these ideas. And that's what this says. The constant negative 87, this is the y-intercept. This is the value of the response variable when the explanatory variable is 0. Check the context of this. Often it makes no sense. It has no such value. In this case, it is not possible to have a volume that is negative, nor is it possible to have a height of 0. All right, and then you guys already told me this. The slope. This is the coefficient to the explanatory variable, and this is the slope. The entire line deals with regression for the slope, so I want to tell you that the importance of this chapter primarily deals with this line. This chapter is about slope. Okay, and slope is a relationship between two items, and we're talking about the slope. So this entire line, we will know what that entire line, all those numbers represent. All that we know so far is this 1.54. Okay? But we will learn what these other things mean. Alright, so there we go on that. Prediction equation, you guys already told me that. So here are the two new things for this unit, and this one right here, standard error coefficient, is 0.3839. Let's locate that up here in this. Okay, where do you see 0.3839? Do you see 0.3839 on the printout? Okay, good. Right here, standard error coefficient, and guess what? That is the standard deviation of the slope. So let's now make a visual picture of what that means. First of all, and I actually like the way this is written here. First of all, this is the standard deviation of the slope. Remember that this data came from only one sample. So you got data from one sample, and you made an equation, a prediction equation from one sample. So how confident do you feel that that slope of 1.54 is like perfect, and that is the correct equation for all the trees' relationship between height and volume? Do you feel like that is definitely the slope of the relationship between height and volume? No, it's only from one sample. So therefore, I have some variation in what that slope perhaps really is. That's what's happening here. So the slopes may vary a little from sample to sample. That's what this standard deviation does. And so let's make a visual of this. If this is our axis and we've got height down here and we've got volume here, and suppose this was the equation of our line because we collected our data here, right? So we got the mean point of this line is always a point on the line. 0.3839 means that the slope could be a little more, or it could be that much less. So if this currently is a slope of up 1.54 over 1, up 1.54 over 1, up 1.54 over 1, then if I increase it by 0.3839, my slope might be a little steeper. My slope might be like that. My slope might be a little steeper. It might be 0.3839, so I'm going to be going up 1.8 or 1.9, whatever, over 1. Up 1.8, whatever 1.54 plus 0.389. 3839 is. So it could be steeper. So in the same token, it could also be what? Less steep. Very good. So my line might follow this steepness. This is less of a slope. Okay, so it might be that much less. So that's what the standard deviation of the slope does. It allows for variation. It says, yeah, the slope's around 1.54, but I took that from one sample, and so the slope could be a little more and a little less. Okay? I'm off on how much it could be. Up to that much, okay? Technically up to 3 standard deviations, right? Most of the time it's just going to be, 68% of the time it's going to be within 1 standard deviation. Where did I come up with that 68%? The normal curve. 68% of the data is within, let's remember, if this is our predicted slope, of 1.54, then 68% of the time it's going to be within 1 standard deviation of the slope. 95% of the time it's going to be within 2. And 99.7 it's going to be within 3. Yes. Well, I mean, 95% it's going to be within 2 standard deviations. You're right. And 99.7% of the time it's going to be within 3. So you're right. I would consider probably past 2 as an outlier. But, I mean, it could happen. Okay. So that's what we would expect. It says if we gathered repeated samples, we would expect the slope of the volumes of the truths to vary approximately by this much. All right. Okay. So that's standard deviation of the slope. Our final idea is this value. This value is called the standard deviation of the residuals. Let's locate that on our computer printout. Okay, so here we go up here. Where is this? Good, right here. And it will always be located there. That is called the standard deviation of the residuals. Now, yesterday when we reviewed regressions, we remembered what residuals were, and residuals are what? Good. That difference between actual and predicted, right? Remember that when we did that, we were getting things like this. This would be the residual of the volume. And this would be the predicted, this is the predicted volume with that given height. Okay, remember? And when we make our residual plot. And so what happens with this? We have stuff on either side of it, right? Kind of scattered. Okay? So here's what's happening. These residuals also follow the normal curve. These residuals also follow the normal curve about the predicted line. If this is the predicted line, that's the quote-unquote mean. Watch this. I'm going to draw our normal curve as if that predicted line is your mean. And so guess what? What am I drawing right here? I am drawing 1 standard deviation away from predicted. And what percent of the residuals should fall between 1 standard deviation away from predicted? Good. This should be 68% of the observed are within 1 standard deviation of the predicted. Okay, and what value was that? What were we told the value on this computer printout was? 13.4. So this value is 13.4, and this would be down 13.4. So whatever the units are, going up 13.4 and going down 13.4 is not too much of a worry. Okay? But that's within 1 standard deviation, so that's reasonable. So what would be within 2 standard deviations? Good, 26.8. So how much percent of all of my observed data? So I'm going to have some in here, right? How much am I going to have? Am I going to have the same amount or less? Yeah, I probably have less out here because I am more standard deviations away from predicted. So I'm going to have some out there, but it's going to be less. And so this is 2 standard deviations away. So if I'm 2 standard deviations away, how much do I expect to be contained within 2%? or 2 standard deviations. Good. So 95, tell me what this means. 95% of all what? Observed data. Because that's what these points are, is the observed data. So 95% of the observed data are within 2 standard deviations of what? The predicted. Good. And then we could take it one step further and do the 3 standard deviations, whatever that value is, and that would be just like hardly any in there. But that is 99.7% of all observed. Okay, so that is standard deviation of the residuals. So, in summary, the 2 new items that we had to learn today were this variation in slope. Variation in slope is called a standard error coefficient, and we think of it as standard deviation of the good. And then we also learned that there is variation around this line, and that variation around that line is called the standard deviation of the residuals. Very good. All right, so those are those 2 things that I wanted us to add to this. Now, yesterday